Perfect. And you can hear me well, right?
Yes.
Perfect. Okay, great. So hi everyone, my name is Aliki Kouliasi. I am from the NTUA team, and today I will be presenting the bike sharing rebalancing problem. We do have a real life application in Penteli, so I will just walk you through a bit, give some basics on the living lab, and then some more specifics on the operation, the model that we developed, and the results and conclusions that we came upon. So you've seen the slide before. This is the living lab of Penteli. It is in the northern suburb of Athens. You visited, most of you actually. It is a more special area. It is it's more residential. It's rather hilly. And actually within Penteli, there are, let's say, 4 sub-regions. Having said that, we have identified that it's very important for Penteli to actually find some ways to connect those, let's say, sub-neighborhoods better. There is no rail train within the municipality. There is some railway service, but really in the very edge of Penteli, and then there's mainly bus operating within the area. So the car usage is rather high, and let's say we have different pillars within SUM project. One of the 5 pillars was the bike sharing scheme, because Penteli actually is trying to, let's say, cultivate an alternative mobility culture and promote and integrate lighter modes of transport, and also give the possibility to users to feel included in places that they can go by bike, walking, and not only using car, which is the case today. So these are the 5 main pillars that we are focusing on as a living lab through SUM. E-bike is one of the 5 pillars. Of course, you've seen, we talked about the mass platform and the street space allocation. My colleague Stefanos talked about this, and the mobility hub. So today we will be talking about the e-bike sharing scheme, which is actually running already, let's say, almost a year now. So actually, the idea of Penteli Living Lab is from having these these separated modes of transport, to create one, let's say, more integrated, unified approach towards transportation within the municipality. And of course, bikes is an integral part of this, especially for the first last mile, for the, let's say, around the neighborhood commutes. Therefore, the availability of the bikes is critical for the integration of the service and to create trust in a municipality that's very private car oriented. So our laboratory focused, among others, also on the bike sharing, and we actually deep dive in that. And what we realized is actually, if we manage to kind of shift some users from private car to e-bike sharing, especially in a hilly area, using e-bikes makes it much easier. Focusing on the first and the last mile commutes, we could create a competitive alternative to car if the service is there on time when required from the users. So that's why we said that it's imperative to have effective rebalancing operations to make this successful, to, let's say, cultivate this culture. In order to achieve, let's say, to support SUM goal to switch people from private car use towards other modes, lighter modes, reduce congestion, reduce pollution. So having the bikes at the right time, the right location is essential. And we dealt with this problem. Just to say that the rebalancing problem, it is in the family of the VRP, and it is, let's say, very similar to a pickup and delivery problem. We do have in the area, in Penteli specifically, a truck performing the rebalancing operation once a day. And this is the problem that we tackled. So, of course, we conducted extended literature review on the topic. We focused on the static dog bike rebalancing problem. As you see, this is an actual picture from Penteli. We do have dock stations. It's not free flow, and the rebalancing operation, the requirement, let's say, from the operator doing the rebalancing operations is that the service will happen once a day, every night. Actually, the bikes should be redistributed to the right location. What we realized conducting this literature review is that many research so far assume that the user demand can be fully satisfied after the repositioning operations. Also, only a fraction of the research so far includes the number of bikes to be loaded or unloaded in a station is part of the decision, let's say the decision variable. And ultimately, the effect of geographical distribution of the stations on the routing cost has not been investigated on the rebalancing problem in particular. So this is the Penteli case. This is what we decided to do. So we studied the static dock bike rebalancing problem, where we have as a decision variable the load and unload number of bikes in every station. We give the possibility, because it's a real life case, to have a demand deficit, so to request more bikes than available in a station. This is also depicted in the objective function, where we, apart from the routing cost, we have a penalty for the unmet demand that we're trying to minimize. And of course, we incorporated the impact of the different geographic distribution scenarios in the routing costs. So that's the problem that we are focusing on. I will give some details on the Penteli map, on the Penteli case. So here is the map with the exact six locations of the bikes, the bike sharing stations. Each station has 6 to 8 docking stops, parking spots, let's say. All in all, we have 42 bikes available in the area. And those locations were decided taking into consideration different things. Actually, we wanted them to be around key activities. Of course, we wanted a connection with the mobility hub. You see, the mobility hub is actually one of the 6 locations, is also the same location of the mobility hub, which is actually placed now in the coming month, will be in place. So that it is in the next to points of interest, so people can just take the bike, go around for, let's say, daily shopping or for a workout, for an educational activity, and come back. A bit more detail on the exact layout. I'm just giving an example here of the mobility hub to see how the areas are distributed around the mobility hub. In red, you see the shopping retail activity. In yellow, we have the residential areas. In green here, we have some common spaces. In blue, we have educational, recreational activities. So that was the concept that we have decided all these 6 locations in order to combine actually those key elements. Next to that, we have already created some proposed cycle streets. Here we only have so far around the mobility hub. So that in order to help people and promote bike riding, the cycle streets that we have developed here actually include one-way streets. We've made some circular routes that people can easily go around without a large slope. As I said, Penteli is a hilly area, so it was important to find those locations around the mobility hub and around key activities, and with low car impact. So people are, let's say, we cultivate a bit more the culture of using the bike instead of the car, which is the most important. So now I will be moving to the model. I will try to be concise and not bore you. As I said, it is in the same family of the pickup and delivery problems. Here what we did is that we formulate, I will just go directly to the model, we formulated the model. At the beginning, it was non-linear, it was just a mixed integer problem that we later on linearized. I will just quickly go through. In the objective function, as I said, there are two components. There is a component of routing cost and the component of the unmet demand, the penalty of the unmet demand. As I said, we do have one vehicle performing the operations in the case of Penteli, but we also tested a larger case with more vehicles that starts and ends up the route from a depot. It was a requirement from the bike operator that each bike station is served at most once by one vehicle, so they don't do unnecessary routes. Of course, we do have a flow consultation in the notes, a subtour elimination, so we avoid having closed loops. We calculate with this constraint the number of bikes to be loaded on a vehicle. We always need to respect the vehicle capacity. In particular, in the case of Penteli, we do have a capacity of 12 bikes. Just continuing with the formulation, it's a lot of functions, just bear with me. We do calculate the number of available bikes to be loaded and unloaded in every station. We also determine if whether station is a load or unload station. Of course, we cannot have both, otherwise, it's not possible that a station requires bikes and has excess bikes to give. Of course, we need to respect the parking station capacity. As I said, it is 6 to 8 bikes per station, and we always calculate the status of a station being served, and this actually is used then in the objective function to see whether we have unmet demand that needs to be penalized or not. That was the mathematical formulation. I also have some extra, let's say, I do have the linearization of the model, because if you noticed, the objective function had a non-linear component that we had to linearize. So we have introduced some auxiliary variables that, of course, introduce some extra complexity in the model that it is already a bit hard. But using those extra auxiliary variables and those extra constraints, we managed to linearize the objective function. Similarly, the non-linear constraint about the number of bikes to be loaded or unloaded is linearized again by introducing a big N. And some more constraints that they were non-linear linearized using the big N formulation. As I said, this problem is an NP-hard problem. So in order to reduce the size and to ensure that the optimal value or a tighter lower bound can be derived within a time limit that we set. We set a time limit of 2 hours, so it is reasonable to run it daily. We introduce some valid inequalities. Actually, the subtour elimination constraints that I talked about earlier, we introduced them as lazy constraints, meaning that those inequalities, meaning that those lazy constraints are actually only used in the case that we found a new solution. If a new incumbent solution is found, then this solution is checked against feasibility, whether it forms subtours or not, and it calls the lazy constraint then. So we don't introduce them always, because we realize that it expands really the computational time grows exponentially. So that's why we introduce them as lazy constraints, and then we introduce those valid inequalities that they are only applied in the case that the demand of a station can be fully satisfied, and they are proposed and applied in this case, so that we actually try to tighten the model, the base model, and improve the convergence to the globally optimal solution. These were the steps that we took to reduce the model, and now we have the computational results. Actually, here we run 3 different case studies. The first one was a small data set, a small scale problem. We ran a towing network of 5, 8, and 10 bike stations respectively to see how the model reacts, to actually assess the performance of the proposed heuristic algorithm, and actually validate the results. In this case, we've seen that the instances of 5 and 8 locations respectively were quickly solved, but from 10 stations onward, the time required from the model to solve it to optimality grew exponentially. Nevertheless, all instances were solved to optimality, and we even tested the negative demand. So we tested different cases of positive, 0, and negative demand, meaning positive demand, we have more bikes than available, 0, exactly the amount of bikes with the demand, and negative, we have higher demand than the available bikes, which is let's say, the most demanding computationally. So this benchmark, this small scale example was used as a benchmark to validate our heuristic, and then we moved to the other small case, which is Penteli, because I said we only have 6 bike stations. Here you can see the demand from the starting points and respectively the destination points for the period that we have the available data. Because it's a small scale problem, the problem is actually solved to optimality in under 1 second. And we are using the actual locations, and we calculated the Euclidean distance among the municipality's bike sharing locations. And then to test actually the performance of the model in a larger scale, we used a second data set, which is actually taken from the literature. It is taken from Santori and Buriol, where we solved instances of 12, 15, and 20 bike stations respectively. And these are actually coming from real locations from Barcelona, Berlin, New York, and Porto Alegre, where we actually tested the impact of different geographic distributions, random clustered, and entirely clustered distribution of the stations. Here we also impose the time limit of 2 hours, so that is realistic to run it daily. And actually, after running that, we ran both cases of positive and 0 demand. Once again, I'm saying positive demand means we have more bikes than the demand. We have more bikes available than the demand. We've seen that actually for 12 stations, we obtained the solution into 5 seconds to 6 minutes, so rather quickly. The computational time required increased exponentially in the 15 and 20 bike stations respectively. And of course, we've seen that the routing cost decrease in a more clustered geographic distribution. All in all, most of the solution was within the time limit of 2 hours, but in the 20 network, which is the most, let's say, demanding computationally, the most complex, we even had a gap of 10 to 30% sometimes. And here is when we realize that this is an NP-hard problem, and solving it exactly, it's very demanding and requires a lot of time. So there is an upper limit, in our case, the 20 stations. In the same dataset, we also checked the possibility of zero demand, so having exactly the same amount of bikes available as the demand. This is a bit more demanding computationally because you don't have abundance of bikes anymore. In this case, we had slightly larger times into the small instance of the 12 stations. When the bike stations were randomly distributed around the depot, we realized that the routing costs are higher compared to the clustered ones. And in this case, for the 20 bikes sharing station locations, the average gap is around 20%. And as I said, this is more demanding computationally. All in all, after solving the MILP, linearizing the problem and solving it, incorporating the routing costs and the unmet demand, after running several tests, the upper limit of 20 stations was reached. The performance, of course, varies of the routing, and the routing costs vary under different geographic distributions. When the bike stations are positioned in clusters of central urban regions, the installation and operation of the depot facility in intermediate points can bring significant cost savings. This is what was came from the computational results. All in all, we've seen that in the case of the positive demand, having abundance of 5 more bikes, the random versus the clustered incurred larger differences. These differences are varying from 10 to 36% higher when comparing random versus random clustered. And when comparing random to entirely clustered networks, this difference is can be from 25 to 100% routing cost higher in a random case versus a clustered one. For the zero demand, very similar pattern again. We see that the random cluster behaves better than the entirely random distribution, and the entirely clustered, of course, even better. We can have savings up to 90%, up to 90% higher cost in a randomly distributed network versus a clustered one. And in most of the cases, this difference can be more than 50%. So it is a significant saving. All in all, as I said, because the rebalancing problem is an NP-hard problem, we managed to solve up to 20 stations. Of course, this remains as a next step for our future work to develop efficient metaheuristic algorithms to be able to solve even larger cases. And we are already even in discussions with the Municipality of Athens to approach a similar problem. And of course, in another case, actually in the case of the Municipality of Athens city center, it's not necessarily a docked system. We solved the docked system because we had these very specific 6 locations with 6 to 8 parking spots, but in real life, solving the problem dynamically in a free-float network would be a bit more realistic. So this is in the outlook for the next steps for our team. And yeah, actually that was all. Thank you very much for. And of course, if you have questions, please reach out.
Thank you so much for the presentation. I think Yaron had a question. Or was it by mistake?
A few technical issues to understand the context. You have 42 bikes. Are some of them electric or all of them? Or?
All of them electric, yeah.
Okay. And how many people live in Penteli?
In Penteli, it is around, I would make a rough estimation because I'm not sure 100%, but I would say around 4,000. It's a very rough estimation. I should definitely look it up.
In your algorithm, was there any difference between different days, or it was a set algorithm? So, for example, holidays, weekend, I don't know, festivals.
No, we actually did. Here we just had the full amount because we have very limited period of data in Penteli case, right? It's less than a year, and it's, as I said, it's still the cultural obstacle because people use a lot of cards. So it's really in the perceptions of people to start using the bikes. It's a bit tough. So we don't have sufficient data to make this breakdown into, let's say, different days of the week or weekdays, holidays, etc. So we haven't really done that so far.
And technically, again, not regarding the algorithm, you have like one car operating the entire system, and how many hours a day this car moves, like moving bikes, operating, fixing.
So that is a requirement from the bike operator, and that's why we also approached it like that in the Penteli case specifically, that they want to run the operation once a day. So every night they want to make the redistribution. That's why we call it static. That is the meaning of static. That the rebalancing operation happened once a day.
And I will, sorry for asking so many questions, but
no, feel free.
The eastern part of Penteli is a forest.
I can go back to that just quickly.
Because we were in the municipality, I don't know near what station it is, but I see that all the stations are in the western part.
Yeah, so if you see here from the entire eastern part is actually the hill. There are residents, there are houses, but it's not very dense. So the most of the activity happens here on the left-hand side, on this left-hand side area, and this is where we have also the locations, because if you see here, it's mainly mountain.
Because of touristic issues, like is there a line for bikers to go through the hills, through the forest?
There is no designated line in Greece in general, and the routes that we have at the moment, the routes that we have already developed are in the, let's say, in the western part of Penteli, around the mobility hub and the most of the shopping activity, recreational activities. For the mountain, actually, there are bikers going riding in the mountains, but it's not, let's say, in an official route that they follow, if you know what I mean. It's the cycle streets that we have created are actually more on the west side of Penteli here.
Thank you.
Thank you so much for the questions, Yaron. Are there any more questions? Feel free to ask directly. Okay, it seems like we don't have any further questions, so I will stop the recording now.